First, we need to identify the scientific subgraph. Scientific subgraph is a bridge between time that represents the wall lobes and depth that represents the seismic section. Time converted words by check shot, data, and sonic lobes. We're going to use the check shot and sonic lobes to convert the words from time domain to depth domain, so we can calibrate and get the surfaces of our object. Generating seismic seismogram from density logs, sonic logs, and seismic wavelet by calculating acoustic impedance and reflection coefficient, which are then convolved using a wavelet. Here we use a Reservoir equation to calculate the acoustic impedance and reflection coefficient. That would help us identify the seismic tools. As you can see in the first track, represent the sonic log. The second track represents the check shots. Third track represents the density logs. Represent the correction sonic log. The fourth track represents the density log. The fifth track represents the acoustic impedance, and the sixth track represents the reflection coefficient. Here, the seventh track is a slice from seismic that going around the well, which is well 292. And here in the track 8 is the extracted synthetic seismogram that will help us in identifying the well tops and depth domain. Here, as you can see, the synthetic seismogram has been done for well 292 and 17. We use only two wells because they are the only wells that has sonic logs and density log. Without it, you can't manage to do the synthetic seismogram. Here, as clear, these points represent the well tops. As can you see here, without the synthetic, you can know where the area you should draw in your project. So, first step is making the synthetic seismogram. Second is realizing the volume. This step is important because it can manage and saving a lot of time. Realizing helps to create a physical representation, which will save the seismic cube in the project. You don't need to load it each time you start the project. And can achieve the value resolution. It will lower the resolution and lower the size, so you can move and make the interpretation track through each line and X-line more faster. Realization change how seismic data is handled. It can be easy to handle. Realization increase memory loading speed. As I said, it helps to lower the volume of the RAM, so the device won't crash through interpretation. Interpretive horizons, due to the poor quality of the data, the interpretation had to be fixed manually. At the beginning, we tried the auto-tracking technique. We tracked the member 5 VB, member 3, member 2. But due to the poor quality, the auto-tracking couldn't be managed because we have a problem in member 3, we'll show you later. It keeps disappearing and appearing. So we had to fix the auto-tracking by going manually through each L line and X line, which represent like 500 L line and 450 X line. And this process really took a long time. Here, as you see, the X line. In blue, showing the member 5 AB. And in white, showing the member 3, which is, as is clear, you see, it keeps appearing and disappearing here, like sort of patches. And in member 2, and this member 2, we had to assume it, because we didn't have the wall tops for it, so it's not sure if it's member 1 or member 2. But we needed to limit the volume, so it will help us in, later on when we put the water oil contact. It will fix a lot of problems, like we don't need to, it can be calculate the volume by adding the water oil contact. It will be shown later why we had to assume the member 2. Here the same for the X line. As you can see, member 5 AB, member 3, and member 2. Here showing fast forward video showing how interpretation done through the L line. And the same goes for the X line. For 500 L line and for 1500 X line approximately. Here, the member 5 EB. when you put the L line and X line together, when you cross them, they represent a point. As can you imagine, when you put each L line of 500 L line and X line, you put each L line and X line as a crossover, you get points. These points could be called grids. These grids help you building this model or this surface as a horizon in time, as a grid. And this is the member tree. As can you see, there is a lot of patches keeps on disappearing and appearing in the middle. This will cause a problem later on in identifying the 3D grid. Causing this problem will not the 3D grid, and we created later. We use a simple 3D grid. Will not cover perfectly the surface. Here, the member 2. And here showing the 3 members stacked above each other. As can you see, the highs and lows. The high is represented as green color, or a blue color, sorry. I mean yellow. And the middle represented as green. The lower is light blue, and the dark blue is the lowest area in our horizons. Second step, we need to create the surfaces. What surfaces and what is the aim for creating it? The aim of this operation is to provide a quick indication of a surface geometry that is being developed. As can you see, when we created the horizons in time, it represents as 3D points, which will take more time to load, and this surface will take each point, or maybe 10 points, and draw a surface for it as an average. So it will help us in defining the 3D grids, and it will as an input for mostly everything in our project. The input data is for creating the surfaces is you can use bitmaps, horizons, points, lines, surfaces, well tops, and properties. For our step here, we used horizons that has been interpreted, and we used well tops as colorating the well tops. The boundary is a closed polygon that you create to close the area. Because if you didn't close the area, the surface will reach out of the area, and this step won't be necessary. As can you see here, the surface for member 5AB. This step has been, we created the surfaces, and the first, the surface before the smoothing, this process after the smoothing of the surface. Before the smoothing, the surface will have a highs and lows, which represent like mountain hills. Would cause a lot of problems. The surfaces will intersect each other. That will make a poor quality of 3D grids. So we had to average it, and it will look like a much reliable case and much reality. Here the member 3 surface, and here the member 2 surface. And here the 3 members stacked above each other. As can you see, the highs and lows. Chapter 5